Hey, so welcome to this UVM sequence item sequence sequencer and the driver part 2. So we have already looked at the sequence item, how it is used for modeling the transaction as a part of this series in the part 1, and as a continuation in the part 2 we are going to be looking at sequence, sequencer and driver, and what are the various communication models and what are the different ways to model these sequences. So we'll continue with that in this session. So we have looked at the sequence item and how to use the UVM sequence item to model the transaction, like how we can write the different functions that can be used by the different components within the test bench, and how it satisfies all three requirements of being able to generate the stimulus, and being able to drive it, and being able to monitor it, and in the scoreboard how we can use it for the comparison, and then how while debugging we can print it. So all angles we have looked at it from the looked at the UVM sequence item, which is nothing but a transaction, which is the basic communication element. Now next what we will do is we will move on to the next items, that is how to use this UVM sequence item for doing the stimulus generation, which is our which is next primary goal for this particular session. So we will look now at the sequence, sequencer and driver and their interaction, and we'll build further onto it. So let's quickly define each of these elements. So sequence, as we know, it's like a primary means for generating the stimulus in UVM. Then both the sequence item as well as sequence belong to the object hierarchy in that overall UVM base class diagram that we had seen. Both the sequence and sequence item belong to the object hierarchy, and they can be randomized to generate the interesting stimulus. Tests use the different combination of sequence from the sequence library to generate the scenarios, and the sequences run on a sequencer, okay, and then that's how they access the test bench. And sequences randomize the sequence item, and they send it to the driver via the sequencer, and then driver converts the information in the sequence item to the pin level activity. And then sequences can also be randomized, by the way, right? It's not that only the sequence items are randomized. So sequences are randomized to set the like for example the range of values that, let's say, a sequence item can take, right? Or the number of sequence items that we want to generate in the sequence. So both the sequence and the sequence item can be randomized. So you randomize a sequence in the context of test and then start it off on a sequencer, and then the sequence again randomizes the sequence items and passes it to the driver via the sequencer, and then the driver will drive it out on the interface, right? And then the sequencer, so what's the role of sequencer in all this process is, sequencer is an intermediate component, and it facilitates these two things. One is it defines the communication protocol between the driver and sequence, which is something that we will look at it in much more detail. And then you can actually run multiple sequences parallelly on a single sequencer, right? So sequences can be run parallelly on a different sequencers, but multiple sequences can be run parallelly on a single sequencer, which can create a mix of traffic, and then the sequencer does the job of arbitration. And there are different arbitration schemes that are provided as a part of the sequencer. Sequencer is component, by the way. So it arbitrates and selects the sequence item from different sequences, and then passes it on to the driver. So the communication protocol between your sequence and driver is controlled through the sequencer. And second, I can be running multiple sequences on a sequencer. It does the arbitration before passing it on to the driver. And then the flow of data between your sequence and driver is bidirectional, and that is facilitated by the sequencer. So we look at how all of these things work in much more detail in the next few slides. We'll start off with looking at how the communication between the sequence and the driver can be modeled. Although the sequence and driver handshake for the data flow is a very flexible and it's a bidirectional, but there are different models that are generally used in the real life application, and implementation of these requires using certain combinations of APIs, and in few cases you might have to build the additional tracking logic as well. So the different types of communication mechanisms that can be utilized is, the first one is a simple unidirectional protocol. It's typically non-pipelined and unidirectional, and only requests are sent from the sequence to driver, but there is no response received back from the driver. So this is a simple unidirectional flow, and one typical example bus that you can utilize this type of the unidirectional data modeling is the AXI4 streaming bus. So it's called AXI4-S. It's not a AXI bus, right? It's a special bus called AXI streaming bus. So it's just a unidirectional bus based on some like a valid ready and a data type of a signal. So those type of buses they can be modeled using this type of a the data modeling. We'll look at it like how the combinations of APIs are used, but first let's define what are the various models that are possible in the real life applications, and then we'll map these models as to how we should utilize the different APIs to implement each of these models. So then we have a bidirectional non-pipelined. So bidirectional request and response exchange flow takes place, right? So sequence can send a request to the driver, and driver can do something and send a response back. So there is a bidirectional, but it is non-pipeline. That is what that means is the response occur in lockstep with the request. That is, the request completes and then only the corresponding response is sent back, and then only the next request starts off, right? So the request and the response themselves they are executing in a mutual exclusive way. Not only that is happening, that only after this full transaction flow is completed is when the next transaction is getting initiated. And what this means is that between your sequence and driver, and there will be only one request that will be active. So only after that completes is when the next request gets generated. And simple example is your AMBA peripheral bus APB. APB protocol is a bidirectional non-pipeline model. So then we have the bidirectional pipeline, and where there can be in order responses. So bidirectional request and response exchange flow takes place between your sequence and driver, and pipeline implies here that the request phase of the current transaction can overlap with the response phase of the previous transaction, right? So you're understanding, right? So let's say I have a request bus and a response bus. So now both are getting utilized, right? In the APB, what happens is we have like a PR data, PW data type of a bus, and but only one of them is getting utilized, right? So the other one is just sort of like idle, right? It's not getting utilized. But when you do the pipeline type of an bus protocol implementation, your goal is that you want to improve the overall efficiency of it. So you keep multiple transactions active, and when certain combinations of the transactions takes place, the entire bus can be kept utilized, right? So that is the whole idea of doing the pipelining. And then pipeline improves the hardware performance as well, because of the hardware utilization improves. And then but this overall process leads to some sort of complications because now request and response have to be handled separately, right? It's not that we can send one request, wait for the response, and then only we are initiating another request. It's not like that. We are sending the requests uninterrupted, and then the response is coming in separately. So we can't like wait for one request to complete and then only send the next request. So that changes how to use the APIs that are provided. And then you can have bidirectional pipeline with out of order response is another variation. The pipeline response is coming out of order. So when the request is issued, it's acknowledged that it has been accepted, but the response to outstanding request may be sent in different order than they were received, right? So what happens is I might send up to, let's say, I can say outstanding requests that I can handle in a pipeline bus, let's say up to 16. So I can keep on sending up to 16 requests without receiving any sort of response from them, right? So I am not received any response, but I'm just sending the request. So then what happens is when the responses are given out, the responses can come in any order. That is, the 16th request might get first response, and then thereon, like maybe the first request response might come out. So they can come up in the jumbled order. And in such scenarios where you can receive out of order responses, the protocol itself, not our sequencer or the driver type of protocol, I'm talking about the, like, let's say PCIe protocol, for example, right? So what the protocol will do is it will implement some sort of a ID mechanism that's provided as a part of the request, and then when the other end sends back the response, it will use the same ID or a tag so that we can relate them. Although they come out of order, I know which response belongs to which request because I have the common tag or a ID between them. And note that this mechanism is sorry, for example, when we discuss the sequencer, like briefly we have seen a little bit about it, that there is a concept of like the sequencer will stamp a sequence ID and a transaction ID for routing the responses. This is different. Okay, so this is inbuilt usage. This is for the inbuilt usage of the sequencer, and these IDs that it stamps are private, whereas this out of order responses that I'm talking about, these out of order responses have to be built in as a part of the external protocol that we are implementing. The protocol itself is out of order response based pipeline protocol, and when such protocol exists, it has to provide the additional the IDs or the tags through which the responses can be correlated, which are different from the sequence ID and the transaction ID stamped by the sequencer for its own routing, right? So those are two different things that you might want to keep in mind. So we have, in summary, we have a unidirectional, we have bidirectional pipelined, the bidirectional non-pipelined, and then we have bidirectional pipelined with in-order responses, and then we have bidirectional pipelined with the out of order responses. So these are some of the real life use cases that I'm talking about. Now, how to model such things using the APIs provided by the sequencer and the driver, we will look at it in the next few slides. So this is the way overall like a sequencer and driver would appear. So we have a sequence which creates the series of request sequence item and reads the responses. That's what the sequence will do, and then it can communicate the request to the sequencer, and then the sequencer talks to driver over this sequence item pull port, and then driver drives it out on the DUT, which converts the transaction to signals, and then any responses that are being driven from the DUT, it converts those into transactions, and then it has an analysis port which it uses as a response port, and that is sent back to the sequencer. And the sequencer, what it does is, while sending the sequence, it stamps them some sequence and the transaction ID in the request. So the driver is expected to stamp them back while sending the response, if it is sending it as a separate response through this analysis port to the sequencer, so that the sequencer can take it and route it to the appropriate sequence. Of course, if we are running only one sequence, it doesn't matter much, but if we are running multiple sequences, then each of the sequence wants to wait for a specific response that is being sent to the request that is created by that particular sequence, then this ID based mechanism, which is a built-in mechanism of the sequencer, becomes important. And so let's formally define all these things. So the flow of data between the sequence and driver is bidirectional, because we have this bidirectional communication. The request can go through the sequence item pull port, and the responses come via the analysis port, right? So these two information that you might want to remember. So request move from the sequence to the driver, and the responses moves from the driver to back to the sequence, and the driver and sequencer are connected through the sequence pull TLM port, and then the sequence item are randomized within the sequence. That's something that we have already defined, and the sequence and can also contain random properties which we have specified. So these random properties could be further used either for generating some number of sequence items, or can set some sort of a limits for generating the limits for the properties that are used within the sequence item. So sometime even for those you can utilize, like for example, I want to generate length between, let's say, 5 bytes to 32 bytes, right? So let's say I want to restrict all the sequence item that this particular sequence is generating to the length of 5 to 32 bytes. That length I can randomize within the sequence, and I can use that for constraining the sequence item that I'm generating with the help of inline constraints, right? So I can do that. So that is the reason the sequence can also contain the random properties, and sequences are randomized either inside the environment or typically inside the test, because test is what is responsible for creating the stimulus, and it creates that stimulus by picking up various sequences and then running them on the sequencer, and then those sequence item requests go for via the sequence item pull port to the driver, get driven out on the signals. The responses are collected by the driver, and they can be put in the analysis port back to the sequence. Now I am showing you the bidirectional communication model, how it is natively built in, but there are different ways of implementing the bidirectional response passing, which we will look at it further in the examples. Okay, for the sequencer and driver communication to work, as we showed in the previous slide, all of them have to be parameterized with the same type of sequence items. What do I mean by that is, let's take a look at it. So here we have a sequence driver and a sequencer, right? So the APB sequence extends UVM sequence, and it is parameterized by request and response, and by default, if you do not specify explicit response will be equal to request. I have not shown it over here, but in the declaration of the UVM sequence base class, the response is equal to request. So but here anyway, we are specifying the parameterizing it with the type request is equal to request underscore t, and the response is equal to response underscore t, with the two different request and response sequence items. And then the APB driver must also be similarly parameterized with the same request and response, and the sequencer must also be parameterized with the same request and response. So the parameterization must match, the driver parameterization must match with the sequence, and parameterization of the sequencer must match the driver and the sequence. So all three of them, when they are parameterized with the same the request and response, then only the communication that we showed in the previous slide would work. Additionally, as we have seen even in the examples, the sequencer, right, is mostly a boilerplate code. There is not really any user defined code that is required unless and until you intend to add some additional tasks or functions to it. So if you aren't planning to do that, then you don't really need to write that sequencer boilerplate code. So you can just use this macro. So if you say typedef UVM sequencer, and with whatever the parameterization, if you say APB sequencer, that's more than sufficient, and there on you can create the sequencer and use it. So you don't have to write that boilerplate code. So just using this typedef, you should be able to utilize the the sequencer handle, and then create the object and be able to use it. Let's look at a little bit the inner details. So we'll go deeper and deeper to the examples now. So let's quickly look at it. So we have sequencer and driver, and as we have seen in the previous slide as well, that they are connected through two TLM ports. So there is a one UVM sequence item pull imp that's present within the sequencer, and a UVM sequence item pull port that's present within the driver, and these two need to be connected, and this is the path through which the requests flow. So what really happens is actually the driver that pulls the sequence item via the sequencer and from the sequence. So that's the way communication works. So this is the pull port that gets utilized for that, and the second TLM port is for the response communication, and that's the of the type UVM analysis port. And then the sequencer contains the UVM analysis export, and through this the sequence can extract the response. So there are different ways to send the response, and one of the ways is that you can send it via this response port, and then that can be extracted from the sequence. So we will look at it now. Overall, when we put all of this together, so anyway, we know that the driver and the sequencer are connected through these two TLM ports. Additionally, within the sequencer you have two FIFOs. So there is a request FIFO and there is a response FIFO, and on the request transmission side from the sequence to the driver there is an arbiter, and this arbiter is the one that arbitrates if there are multiple sequences running on the sequencer. And then there is a routing logic at the output of the response FIFO, and this route logic will be active when the sequence says get response to a specific type of a request, right? So when we look at the example, we will show you that you can specify a specific ID. When you say get response in the sequence, you can say that I want the response for this specific request ID, and then the route logic will make sure that it will route that particular ID to the sequence. Otherwise, by default what it does is that it will route the corresponding requests that are issued by the corresponding sequences, right? So if a particular sequence has, like when you have multiple parallel sequences running, whichever sequence has issued whichever request, the corresponding response to them gets routed to the corresponding sequence in order. That's one default mechanism. Additionally, this can hold the response, and then the sequence can wait for specific responses, right? So that is another mechanism that is allowed, but in the process there is a possibility that this response FIFO can overflow, and in which case the warnings get issued. By default, I think both the FIFOs are sized to a value of 16, and now the overall, as far as the overall interaction that is concerned, it happens through these bunch of APIs. So sequence uses this API called start item, finish item, and get response. The get response is the one that is used for getting the response, and then the on the driver side you use the API is called get next item, item done, and then item done can be has two flavors. Item done can be just done without passing any value, or item done can be called by passing a response to it. And then we additionally have like write API, which is the API of the TLM analysis port. So you can say response port dot write. Response port is the handle for this UVM analysis port present within the driver. So you can say response port dot write and pass the response. Along with this, one form of communication, and another form of communication is it can do get and then put type of interface as well. So it can say get request and then put response. Both have a different way of establishing synchronization with the sequence via the sequencer. So how these APIs get utilized, so we'll look at it in the next few slides. So we have broadly understood the like a sequence, sequencer, and driver, and the like what is contained in the sequencer we have seen, and how sequencer and the driver are connected together we have seen. Now before we jump into the actual examples, let's just look at this one last detail of how to pass the response, and then we'll jump into the some of the real examples. So in any bidirectional mode of communication, when you want to implement unidirectional is not a big problem, but when you want to implement any bidirectional mode of communication, the response needs to be sent back to the request. and the response to request can be communicated in two different ways. One is the response fields can be modeled as a part of same request transaction, right? So if you remember, we showed that both the like all three, right, the sequence driver and the sequencer must be parameterized with the same request and response sequence items, but you can parameterize it with only one, right? And then the response type will automatically infer that it is of the type request. So let's say we are using only a single sequence item, and in that single sequence item we are declaring fields both for the request as well as the response. That's what this particular first mode of usage means. So same object is used for both the request and response, and then the request fields are randomized and response fields are not randomized. That's what it is. And then the response is modeled as a separate transaction. That is the second mode of communication. So when you do the first mode of communication, wherein the request and response are modeled through the same transaction, then what happens is the response FIFO path in the sequencer is not utilized, right? So if you remember, between the sequencer and the driver, there were two TLM ports. One was the sequence item pull port and another one was the analysis port. So when you use the same sequence item for sending the request and as well as getting the response back, the analysis FIFO path for the response port is not utilized, and both the request and response handshake phase are still completed. So when we go further, we will see that the communication between the sequence and the driver via sequencer has two phases. In one phase the request gets communicated, that's the phase 1, and then in another phase where the response gets communicated indirectly. So both the phases needs to be still completed, even though you are using the single UVM sequence item for sending the request as well as receiving the response through the same sequence item with the additional fields added for the response. So after the response handshake phase completes, the same request handle that you had created can be accessed to process the response field. So this is an important point. What it means is we have a single object, right, and that single object contains fields for request and contains the fields for the response. So now through the first level of handshake, what we have done is we have passed on the request from the sequence to the driver. Now driver drives it, and while the driver is driving it, although the sequence has the access to this request handle still and can access the response field, but the response fields are not valid, right? So now the driver will drive the request, get the response, populate the fields that are present within the same request object with the response information, and then initiate the handshake to communicate the response response, like the response fields being populated, right? So it will initiate the handshake, and after the handshake completes, nothing really needs to be exchanged because the sequence already has the handle to the request object, but it understands that now it's okay to access the response fields that are present within that request object handle, right? So then it goes accesses those response fields. So the response handshake tells the sequence that now it's okay to access the response fields, right? The time validity is established through the handshake mechanism. That is why both the handshake phases must still be completed, although we are not really exchanging a separate response transaction. And how that handshake is established, that we will look at it in the next slide. And the second mode of operation is that response is modeled as a separate transaction, and when it's modeled as separate transaction, then anyway you have like one request sequence item which is extended again from UVM sequence item, and then we have a response sequence item which is again extended from the UVM sequence item, and then the driver will really create a separate response sequence item and then send it via the response analysis port. But via sending it although it sends via the same the response analysis port, there are two ways in which it can do it. So one way is that it can use that sequence item port from which it is pulling the requests, right? It can say sequence item port dot put response and provide the response. Even though it does it this way, finally it really gets routed through the your response FIFO itself, the common whatever the response path we have, it gets routed to the through the same path. It ultimately is just a two ways of doing things, but both of them they send it via the response analysis port and the response FIFO. So one is the driver can do sequence item port dot put response and pass the response, or it can do like the response transaction communicated directly via the analysis port driver using response port dot write and response. But if you internally look at within the UVM code of this, it will again come back and do the same thing, right? But there are two ways of doing the same thing. As we have been discussing, there are always multiple ways for doing same things. Why I am telling you this is sometimes you can see this form and sometimes you can see this form, so don't get confused. In either of them, what essentially is happening is we are sending it out as a separate response as the first part, and second part is you don't really have to worry about it, but if that sort of like to just to have that understanding, that know that it is really going through that analysis port and through that response FIFO within the sequencer, it is reaching to the through the same path, it's reaching to the sequence in both the cases. So I think we have sort of understood how the response can be passed in both the forms of modeling for the bidirectional type of a protocol. Now let's understand that handshaking that happens between the sequence and driver for both the request and the response phase. Okay, this is the handshake mechanism between the sequence and the driver that happens via the sequencer. So this is the one that is the handshake where we use the common sequence item for sending both the request and the response. If you want to send the response via a separate sequence item, there is one more additional step that gets added to this handshake. But this is the core part of the handshake that takes place, which establishes the transfer of request and validity to response either for the fields which are present within the sequence item or for getting a separate response, right? For both of them, the validity is established through this handshake. So let's understand. So this is an important handshake mechanism, so pay attention to it. And so the data flow takes place through the request and the response FIFO that we have already shown within the sequencer in the form of UVM sequence item, right? And then it's a two-phase handshake. The first handshake, first phase of the handshake is to arbitrate and transfer the request from the sequence to the driver, and then the second phase of handshake is to transfer response from driver to the sequence, right? And that is the two-phase handshake. And then the handshake takes place through the set of API calls between the driver and sequence, which happens via the sequencer. So we had looked at this bunch of API calls, but now we will see how they can be utilized. Okay, so one basic idea that I want to tell you guys. So a sequencer will only route the sequence items from sequence to the driver when the driver is ready. So the driver is the one that is in control over here. Only when the driver says get next item, it's only at that point of time the sequencer will take a sequence item from the sequence and send it out to the driver, right? So let's say now there can be two possibilities. So one is the driver gets ready early and he calls get next item, right? So if he calls get next item, then as soon as the sequence gets started on the sequencer, then he will be able to route a sequence item. But let's say if the driver is not ready, so which is what I'm showing you in this case, and then the sequence starts first. Okay, so now we start a sequence. So the way the sequence gets started is in the test you instance a sequence, and then you say sequence.start and pass the sequencer handle. That sequencer has a physical existence because sequencer is a component and sequence is an object, and that sequencer is connected to the driver via the sequence item port and the response ports, right? So that picture, you make sure you have it in your mind. So we call the sequence.start and we pass this sequencer handle to it, and then when we do that, what the UVM does is it invokes the body task that is present within the sequence, right? And then within that body we are doing calling these API calls, right? And the one on the right hand side where we are showing the APIs called from the driver, these are being called in the run phase of the driver, right? So these are the two things that keep that in the mind. So in the run phase we have a forever loop to take a sequence item one by one, drive it and send any corresponding response, right, and keep repeating that loop. So as soon as the sequence starts, it will call the start item, right? So what it will do is it will create a sequence item handle, and then it will create an object for that using the factory, and take that handle, and using that handle it will call the start item. And once it calls the start sorry, once it calls the start item, it goes to the sequencer, and sequencer blocks this particular sequence until the driver is ready, right? So we call the start item, but it just blocks till the driver is ready, and then eventually let's say the driver gets ready and it calls the sequence item port, which is connected to the sequencer, dot get next item, right? So when it calls the get next item, it tells the sequencer that the driver is ready, right? So after the driver is ready, the sequencer arbitrates and unblocks the start item, right? So now what could have happened is, I'm just showing one start item, but we could be launching multiple sequences on the same sequencer. So all of those sequences will issue a start item, right? They will issue the start item to the sequencer, and then only after the driver is ready, that is the driver has called sequence item port dot get next item, the sequencer will arbitrate among the sequences that are running on the sequencer, and then select one of them according to the arbitration policy that is set, right? So what are the different arbitration policies, that we will take a look at it when we look slightly deeper into the sequencer. So but for this one, so let's say we did this get next item, and then let's say this particular sequence gets selected, then what happens is the start item gets unblocked. Now when it gets unblocked, the sequence item that we had created, we randomize it. So the randomization must be done as late as possible, so as to take the current state of the system into consideration. So you randomize that particular sequence item. Now what you do is, in the sequence body, after randomizing, you call the finish item, right? So you call the finish item, and then the finish item blocks, right? Both of these are blocking type of task call. So the finish item blocks, but the request moves to the driver. So the sequencer now moves the request to the driver for execution, and then the get next item gets unblocked. So the get next item doesn't get unblocked till the sequence calls finish item. So don't get confused that the start item got unblocked through the get next item call to the sequencer doesn't mean that get next item has also gotten unblocked. No. So think of these as two parallel stories running, right? One story is running on the driver and another story is running on the sequence. So on the driver side, the driver is still blocked, only the sequence has gotten unblocked, and then the sequence has randomized it and called the finish item, in which case the request has moved to the driver. That's when the sequencer will unblock the get next item with the proper request sequence item, and then the driver can do the request processing. What do I mean by request processing is that it can take that sequence item, it has all the valid fields because it has been randomized in time, and then that fields it can start driving it out on the actual wires, right? So it can start driving it out, and then after it has done driving, and if there is any response type of a protocol exists, it has done that as well. If that can be atomically completed for a non-pipeline type of a protocol, then what it does is it calls the item done. Okay, and till the item done is called, the finish item would be blocked, right? On the sequence side, it is still blocked for the finish item, and then the item done can be called, right? So then once the item done is called, right, then the finish item unblocks, right, and then the response is actually can be passed. So now item done itself, you can be passing the response which the sequence can extract using the get response, or it can be like passed through that sequence item port dot put response, or the response port dot write. Any one of them can be done. If you want to explicitly send a different response altogether, so that can be done, and that is a point when the get response can be called over here if it is handled through a separate response transaction, but if not, after the item done is called, the finish item unblocks, and then after the finish item has been unblocked, the same request handle that we had randomized, within that handle we can also look at the response fields if we are modeling it using the same request, right? So these concepts what I'm talking about, the actual modeling and then how to do it with the separate response, I think when we take a look at examples it will become more clear. But focus over here from the point of view of handshake that takes place, where each one of them get blocked, how they get unblocked, and when do they get randomized, when does the request processing start. Those are the points that you would want to make sure that it is clear from this slide. Okay, time to put all the concepts that we had seen into practice. So we have the sequence and we have the driver, and then as we talked about, like the driver sequence item port is connected to the M sequencer.sequence item port. So this way this connect is done as the part of the the connect phase within the agent of the APB agent. So as a part of your APB agent session, you probably would remember we had done this. Now let's look at these two pieces of code for how the APIs are used for the handshake. So we have APB sequence, which is extending the UVM sequence parameterized by the APB sequence item. We have a driver extending UVM driver parameterized by the APB sequence item. Both are parameterized by the same APB sequence item, so both of them are compatible. And this is the object registering to object utils, is the component registering to component utils. Not that it matters for the purpose of this discussion, but anyway, so we have the task body as we talked about, which gets executed when we start this APB sequence, and then we have the run phase for this particular driver, where we have the forever loop which executes the request sequence item one by one. So we are creating APB sequence item, and then we are entering the loop, and then what we are doing is we are calling the start item, right? This is what we had done, and then we are passing the request handle. Now this will be going to the sequencer and this will be blocked, so it will wait for the driver to be available to accept the request. And on the driver end, the sequence item port, this is the sequence item port, right, which is connected to your sequencer. So I am saying get next item request, so gets the sequence item from the sequence, right? So this guy gets called, and depending on if this guy was called first from the driver, this would have gotten blocked, and wait till the start item gets called. Vice versa, if the start item gets called first, then the start item will block till it hits the sequence item port dot get next item. So when that happens, then the so when after this line 515 executes, the line 545 which was blocked, if at all it was blocked prior, it would get unblocked, and then we will be calling this request dot randomize, and then if it fails we'll be flagging the error, and then we'll be calling the finish item with the same handle. This is where we are waiting for the completion. This is the sort of the response phase in a way, if you want to say so. So this the finish item gets called, and this blocks over here, and then the sequencer now unblocks this 500 and line 515 which it had blocked, and then this request handle is now the randomized request handle from the sequence, and then we call the drive, and within the task drive we could be driving the request onto the interface, and then at the end, once this drive task has completed, where all the information from the request has been driven onto the physical interface to the DUT, we will be calling sequence item port dot item done, right? So we are calling the sequence item port dot item done. This indicates the sequence item has been consumed, whatever the sequence item that it had received that has been consumed, which in turn unblocks this finish item request call, and then the overall one iteration of the sequence to pass sequence item from the sequence to driver with this handshake has completed. After the finish item has gotten unblocked, then it can move to response phase if there is one, and we can utilize those two methods that we talked about. So let's take a look at the next form of communication. So let's say we want to use bidirectional communication. We in the previous one we were looking at it as a unidirectional communication. Let's say we want to do the bidirectional communication with using the same transaction. That's the mode we want to use. So I am keeping these two same, right? And what we are interested in is how does the response gets passed. So we will only focus from that point of view. What happens is in the driver, when we call the drive request, we get into this task and then we drive the request onto the interface, and after it is driven, right, and like read not write, which indicates that it was a read type of a transaction, then what we are doing is within the same sequence item we also have a read data property to which we copy the bus.read data, right? So from whatever that we have picked up from the bus, this is the response in a way, right? You can think of it like that. So we copy that, right, in the same field. Now when we do this sequence item port.item done, which unblocks this particular finish item, then the response field can be processed. That is, I can say, like for example, after this point I can say $display request.read data. That would be valid. If I say on the line 549, for example, right, if I print the value of read data from the request, it won't be valid, right, because the response handshake has not yet finished, right, because I'm still blocked for the I'm about to do the finish item. So it's only the request has been created at this point of time, right? The request has not even been processed. But if I do the same on the line after the 550, right, let's say I push this end down by one line, and on the 551 if I put the $display and I display the request.read data, then it will be valid, right? So because after the finish item has been unblocked means the response handshake has been completed, right? And what we have done within the same handle, we have copied all the response fields. So this way, using the same sequence item, we can communicate the response back to the sequence. This is the very simplest form of a way to communicate the response or to establish bidirectional communication between the sequence and the driver. Okay, let's take a look at one of the ways to model the bidirectional separate response. So we have this class request response sequence op, which is extending UVM sequence, and then it's parameterizing with the request sequence item and the response sequence item. So we have a request response driver extends UVM driver parameterizing with the same request sequence item and the response sequence item. This is very important for the compatibility. And then we have the body, and then we are creating the request sequence item. Note that we are creating the request sequence item outside this whatever the loop in which we randomize it multiple times and send it. So it's the same request sequence item randomized multiple times and sent. That's what really happens. It's not that we are creating it again and again. Okay. So so the one of the way this method helps is that if you have declared any rand-c type of properties, then that cyclic nature will kick in. But if you keep creating newer objects within the loop, then the cyclic nature will not kick in, because every time a new object gets created, that cyclic state gets reset. Okay. So anyway, that's one point. So let's look at how the interaction takes place for the separate response passing for the bidirectional communication. There are few changes for both the request for both the sequence as well as the driver. So we have start item. This is business as usual. We call request and it gets blocked till the driver pulls the request from the sequence. So instead of saying get next item, we are now using a different API in the driver called get. So we had seen that these APIs are available, right? So we are, instead of saying sequence item port dot get next item, I am saying sequence item port dot get. What's the speciality of this get? Get is functionally equivalent to get next item immediately followed by item done, right? It's a combination of both of them, right? It's a one wrapper that does get next item and item done together. So now what that means? What that means to the sequence, right? So that's what we need to understand. So what happens is that I did a start item, and then once I call this get, which gets blocked till the sequence item is available, and once the sequence item is available, then the start item gets unblocked, and then the sequence gets randomized, and then it will call the finish item, and then the request reaches to the other end, right? But what happens is that the get next item present within the get would unblocked because of that, but immediately it's also calling the item done, which means the finish item would not remain blocked, right? So the finish item would get immediately unblocked after the get comes out. Even the finish item would complete. So on both the threads, so you have to always imagine whenever we are talking about the sequence and the driver, it's a two different threads that are running. So that is something that you have to keep it in mind. So so what happens is this finish item also gets unblocked, but the sequence would now get blocked for the get response, right? The sequence would get blocked for the get response. There are few details, don't worry, we'll come back to that. Whereas the sequence, where the driver will get the valid request which is randomized, and it will proceed to drive, right? And in the drive, let's say whatever it does, the driving part, and then it does whatever the additional processing that is needed to even form the response there itself, or there could be another task that could be forming the response after the drive, right? So after the drive we might have, like, you know, another task that is doing the response phase. That doesn't matter, but let's say it does both of them. It does the request and it also creates the response. In this case, the same task gives out the response. After we have done that, after we have processed the request that we had received and gotten the corresponding response, we call this a particular API called response. Whatever the response, we say set ID info request. So this is the API that we had seen it in the context of sequencer. So this one, what it will do is whatever the sequence ID and the transaction ID that was stamped within the request will now be transferred to the response, right? So in the response handle, it will stamp the same two IDs that the sequencer had stamped, okay? And then if we come back to our sequence, we are saying get response, we are passing the response handle, and then what we are saying is we are saying request dot get a transaction ID, right? So this is the transaction ID we are asking the sequencer to match, and only when that is available we would like the get response to be unblocked, right? So this is an optional argument that you can pass. If you pass it, then it will block till the corresponding matching response arrives. If not, whatever the response, next response that arrives to the sequencer corresponding to this particular sequence, the get response would get unblocked, right? So then the get response, so the get response is now blocked, right? And coming back to the driver, this is anyway a function call, so this will happen immediately while the get response has been blocked, right? Has been blocked for a while. Now what we do is we say sequence item port dot put response and pass the RSP handle. So this will send the response back to the sequencer through that response analysis port, land into the response FIFO which is present within the sequencer, and then sequencer will look at, sequencer would have anyway received this particular call. It would look at an incoming response and sees if the incoming response's transaction ID matches with this particular request's transaction ID, and apparently in this case it will match because we have stamped the same thing, and then it will deliver that particular response to the sequence, right? So and then this get response will get unblocked, and then we will call response.convert string and print this particular information with the UVM medium verbosity. So this is something how it works. We will look at it. Tick UVM info, how this macro works, we will look at it. So this, depending on the verbosity that is passed on the command line, if it is appropriate, then this particular message will get printed. So this way, now if you look at it, both the request and the response handshake happened, and then the response handles validity is established. Only after that we started processing the response. So this is the bidirectional non-pipelined but communicating response through a separate sequence item works. Okay, let's look at a bidirectional pipeline type of an communication or the modeling, how it is done. This is going to be slightly tricky, so pay attention. So first let's understand the problem, and then we'll look at how the one of the solution can be implemented. So the problem is something like this. So we have a protocol wherein we have address and data bus, and on the first clock our address is being driven out, and on the next clock cycle we need to drive up the data. So that's the first requirement. So so there are two separate buses, but on the way we need to drive, whenever we want to drive a request to the DUT, on first clocks we have to drive out the address, and on second clock we need to drive out the corresponding data. But note that when the second transaction's address is being driven out, right, the previous transaction's data one is driven. So so on and so forth. That is the pipelining. Okay. So on the first transaction, we drove out on this particular clock edge, and the corresponding data was being driven out on the next clock cycle. But while the data for the previous transaction is being driven out, we didn't keep the address bus idle. So on the address bus, what we are trying to do is we are trying to drive out the address of the subsequent transaction, and so on and so forth, right? So that is the idea of pipelining, instead of wasting two clock cycles where the address bus or the data bus gets. So here this one is wasted, but subsequently it fills up, right? So we are not wasting the address bus, right? So address bus is another physical resource, so we are optimizing the utilization over here. This is the concept of the pipelining. And let's say that this also, I'm not showing you the response part of it, but let's say that we can get multiple responses back for each of these requests, which needs to be communicated back to the sequence, right? So we have a bidirectional pipeline. So bidirectional, right? So we are keeping it bidirectional because we want to communicate back the response, and we want to communicate the response through a separate handle, and we also want to do the pipelining. So that is the whole thing, to mix up everything to look at one of the complex scenarios, right? So let's start off with the driver. Let's understand the driver a little bit, and then we'll correlate driver and sequence together, right? So this one, since it's being little tricky, we will do it this way. So we have the pipeline driver, extends the UVM driver parameterized by the request and response sequence item. We would need a semaphore lock with one key. How we use it, we'll look at it. We're going to use it for managing the address bus. And then what we are doing is we are forking off do item task, right? We are forking off two instances of this particular task in the run phase for this particular driver, right? So this task run is what we are going to eventually call in the run phase for this particular driver. So what are we going to do in the do item? We are going to come here, and then we are going to do this forever. We have this request and the response handles, but the key thing to note over here is now there are two threads which are doing the same thing, right? So now we launched both of them. Now both of them will attempt to get the semaphore lock, okay, but only one of them will succeed, right? So one of them will succeed. So whoever succeeds now will go ahead and he will say sequence item port dot get, and get, as you know, is a combination of get next item and the item done, right? It's a combination of both of them. So he will do the get. That part of how the synchronization works, don't worry about it. We'll look at it in the context of the sequence. So it does the get, whoever has won, and whoever has lost the semaphore get, he will remain blocked, right? So he will remain blocked. So he will get the transaction, then he's creating a response transaction. In the response transaction, he's setting the ID that was stamped by the sequencer so that the sequencer can route it back to the sequence. And then these were a bunch of additional APIs. I'm just calling it over here just to demonstrate that these exist and can be utilized. So you can call accept transaction. So what happens is when you do this, the transaction internally has few events, right, which are inbuilt, and those events actually get triggered, and those events can be used on the sequence side. If you have a multi-phase type of a protocol, each of those sub-phases you can keep communicating back to your sequence, or sometimes if you want to do any performance measurement, type of an instrumentation, then these events can be used for sampling the timestamps of the key events in the, or the key points in your overall transaction processing. So accept transaction will trigger that particular event. You can either use it or you can drop it. It doesn't matter. As you know, the event triggering, unless you wait for it, nothing happens, but it gets triggered, and then that indicates that transaction has been accepted. And then then subsequently, let's say you begin the activity on your real bus to the DUT. Maybe sometime you might have to wait for grant or whatever it is to start using the bus. You gotten the transaction, you means the driver has gotten the transaction, but it is still not allowed to use the bus. So there can be arbitration involved, right? So if that is the case, then we are waiting for it, and after this particular driver has won the arbitration, then it can trigger begin transaction. Again, that triggers some events back in the sequence item that can be utilized by different components. And what we are doing is, then we are waiting for the the clocking block event, and after that we are driving the address, right? So this is the first clock's address gets driven, and once the address is driven, we are doing lock.put. So now doing the lock.put, what happens is the other thread, right? Like let's say our 610, the task running on the 610 had won the semaphore, the task running on the 611 would have been waiting, and the task running on the 611 will get unblocked when we do this lock.put on the line 635. So he will get unblocked, right? And this particular task will still continue. Okay, the one that gets unblocked on the 611 will do this, has his lock.get has unblocked, and he can now get the second transaction, right? So now we drove on this particular clock edge A1, right? So we drove it over here, and after that immediately we have put it. So on this same clock edge we have put it back, right? And then that lock we have kind of the lock for the 611, that is the second task, got unblocked, and let's say he requested for the second transaction, and if that is available, he comes back, and then on the next clock edge, right, we are on the next clock edge, he that particular the 611th guy is going to be driving the address A2, whereas this particular clocking block, which is the next clocking block for the task executing in the 610th context, the older one which had put back the lock, will now be driving the data, right? So on the same clock edge, now the line number, the task that started through the 610 will be executing the data 1, whereas the task that started on the 611 will be executing address 2 on the address bus, right? And he will do that, and he will put it back, and then this guy will drive the data bus, and he will call the end transaction, and the end transaction will again trigger the event. So there is no handshake that's happening with the accept transaction, begin transaction, or the end transaction calls, but the event is getting triggered. How that event can be used, we will look at it, but the event is getting triggered. So after that, what we are doing, sequence item port dot, we had done put response in the previous case, but you can also use dot put RSP. This also is allowed. So you can do sequence item port dot put and the response. Note that although we are calling sequence item port dot put response or sequence item port dot put, all of them will actually be traversing via that analysis port. Okay, so that is hidden internally. You don't have to worry about it, but know that it travels through that channel. This is the separate response we are sending, and it traverses through that analysis port channel that exists between your driver and the sequencer, right? So we are doing this. So now with this, we have established using this particular semaphore how we are able to accomplish this pipelined type of a driver functionality. Now we will look at it in the context of sequence, not from the point of view of pipelining, but from the point of view of how the handshake takes place in the next slide. I know, slightly tricky, right? So let's continue the next part. So we will now correlate between the sequence and the driver thing that we were doing. So the basic driver structure we have already established. So let's look at the sequence, and once we will sort of match them together. So we have the pipeline sequence. Of course, this request item and response item are matching. We have the body in which we create the sequence. So here we are creating it within the loop. You can notice that that's because we are going to create multiple requests before we get back the response, right? It's a pipeline type of a driver, so you can't use the same request handle for the multiple requests. So because you will be waiting for the response separately, so we need to keep all the separate handles. So we are creating the request within the loop. Okay, for the non-pipeline we could have created outside, because anyway it's going to come one by one. Although it's a separate response, it came one by one. But in this case, we are sending the requests. We could be sending multiple requests, and then at least two in this case, right? So, and then the two requests could be outstanding at any point of time, and then the response will come back. But there can be scenarios where multiple requests could be outstanding as well. In this case, it will be two. So we will say request, we created the particular request, and then we call the start item. And when we call the start item, whoever had gotten unlocked, right, his get will unblock this start item. He will randomize, he'll call finish item, but the get, as you know, does get next item as well as item done. So now the finish item will get unblocked. Now the key thing that we need to notice in the sequence is that it needs to have the capability to separate out the request generation from the response generation. The same thread, right, in the previous case when we had the simple bidirectional case where it was non-pipelined, the get response was called in the same thread context that was generating the request, which was fine, right? So we didn't generate a next request until the response for the request, that the one that we have shared, has come back to us. But in this case, that cannot be the case. If we do that, then there is no true pipelining, right? So if I wait for address to be driven and then data to be driven and then the response to come and then I send the next one, then we are wasting the clock cycles on the bus, right? So we don't want that to happen. So what we are doing, we are forking it off. That's why this is the main thread. This is a request thread. So we are not collecting the request, we are not collecting the response in the context of a request thread. So we are forking off the response, and as we said, the two of the other can have two outstanding requests. So here since we are forking off, this is going to be a separate thread. We are copying the request in the automatic variables. So we will copy the tracking request, and then we will have one response handle which would belong to the thread that we are launching off, right, and then it will be copied to that particular thread context. And within this begin and end, what we are doing is whatever the request for which we are launching the corresponding thread, we are copying that in the track request. We are saying track request dot end event, right? So and this end event gets triggered when this end transaction gets called over here. So only when this end transaction gets called is when this end event gets triggered. So in this handling, I'm not showing how the response is getting collected, but for the ease of understanding this, you can just assume that along with the data phase even the response is collected, right? And so we are waiting for that particular end event, and then you just say track request dot end event dot wait on. This is the event infrastructure that's provided within the UVM, so we are using that. And then this is the API that's provided in the SystemVerilog. Whatever we used to do with it is equivalent to that. So it's going to wait on this particular end event, which gets triggered when you call the end transaction API. And after that we are saying get response, right? So we are saying get response, which would get blocked, and that would be sent via this sequence item port dot put, right? So that would get blocked. So as soon as we send the request, we trigger a thread, we copy that particular request to that particular thread, and that thread will be waiting on the end transaction, and that would be done through this end transaction. We could have eliminated this possibly, right? I'm just showing it to you just to demonstrate that this particular feature exists. And then the get response would anyway get blocked, and that would get triggered when we do the sequence item port dot put right? And then anyway we are stamping the ID over here, so we can pass that request.getTransaction ID, and the sequencer will match it and pass it back to the pipeline sequence thread. So overall, what did we look at over here? So whenever you do the pipeline driver, you need multiple threads both in the driver as well as in the sequence, right? So the based on the number of stages of pipeline, so many number of threads you will really need to manage the pipeline in the driver. And then depending on the number of outstanding requests, so you might have to do the response processing separately. Here per response we are forking off a thread. That's one way to do it. There are multiple ways of doing it. I am not going to get into the details of those at this point of time, but primary point is in the sequence, in order to implement pipelining, you need to make sure that the response phase doesn't block the request phase. That's why you need to fork off the separate threads for them. And in the driver, depending on the number of pipeline stages, there's so many threads you might have to fork off to keep them running parallel, right? Because those have to run in parallel. That's the basic idea of pipeline. And then the synchronization needs to be established between the threads so that they don't consume the resource that's already being used. And for that there are again multiple mechanisms, so semaphore being one of them, which we have demonstrated. So just a quick summary about the our sequencer and the driver interaction. Make sure to parameterize the sequencer driver with the same request and response types. And then the start sequence must be done with the sequence.start sequencer, and then you use the sequence item port or get next item bar item done in driver for atomic access meaning one after another. And you can use try next item done. So this is also another combination that is available. If driver must perform idle cycles, what it means is sometimes even if you are not driving any transaction on bus, sometimes you need to tell idle to the DUT. In sometimes that type could be a protocol requirement. So if you remain blocked for get next item and nothing comes from the sequence, then you have to still drive idle. So in those cases you can do try next item so you don't get blocked. And if that returns false, then you just drive the idle and come back and try again, right? So in those cases you can use this. And you can use either get bar put or put response for the pipeline type of drivers. And then the sequence and driver must agree on the response path, that is whether you are sending it via the same request sequence item or you are sending it via the separate response via the analysis port, so that they must agree upon. So these are some key points to remember. Okay, so we have completed how the different models of communication can exist between your sequence and driver. We looked at unidirectional, bidirectional, pipeline, non-pipeline, then different ways to send back the response from the driver to sequence. So we have completed all of them. Now we will look at what are the different ways that are present to model the sequence for generating the complex stimulus. For a simple stimulus, just a single sequence might be launched from the test, but for complex sequence, these are the various flavors that you could be writing to organize your stimulus generation. One is the simple serial execution, that is one after another. You execute the sequence. Here we are executing A, B and C. We are calling a.start sequencer. So what happens is start is a blocking call, and then that will invoke the body task body present within the sequence A. Until that completes, it will remain blocked, and only after that has completed, then the control will go to B, and then the B will start the execution. Second, you can be doing some parallel execution. So we start the A, and after starting the A, after this completes, we are forking off two sequences on the same sequencer. So B and C are running on the same sequencer. These are the parallel sequences running on the same sequencer, and this is where the arbitration within the sequencer kicks in. And then based on the arbitration type that has been set up, the sequence item from either B or C will be selected and sent to the driver. When both of them complete, it will go to the execution of D. And then you can have a hierarchical type of execution where you call a dot start sequencer, and then this can launch B and C. So the A is parallelly launching B and C, and then B internally again parallelly launches D and E. So this way you have some sort of a hierarchical way of organizing the sequences. So depending on the different type of traffic pattern requirements, you could be doing some of these ways of modeling the sequences. So please note that if you use like a join any or a join none, then you are not recommended to use the disable fork if for the other sequences that are running. That is because that can lock up the sequencer, which can remain incomplete. So you need to make sure that in some way through events or something you communicate back to the sequence that is running so that it can finish gracefully. So that you need to take care. Some quick examples of what we talked about. So here we have a test, we have a init sequence, we have a traffic sequence. Then we are creating both of them using the factory. We are raising objection to hold the run phase, and then we are calling init sequence.start, and we are passing env.agent.sequencer. On the sequencer we are running. After the initialization sequence is completed, we are starting the traffic sequencer on the same sequencer, and then we are dropping the objection. And here only after the init sequence has finished execution is when it's going to move to the traffic sequence. So this way it is executing serially because the start is a blocking task call. So let's take a look at the parallel sequence execution, and we'll use few more features over here. So we are carrying forward the same example, and instead of running them sequentially, we are running them parallelly. Okay, so even though we are running them parallelly, let's try to bring the same behavior, and that we will bring it by using some additional arguments. So typically in the past, what we have been doing is whenever we are starting these sequences, we have been just passing the sequencer handle, but there can be additional arguments that can be passed. So I'm just put the prototype for the task start. So you can pass the sequencer, parent sequence, and then the priority, right? So we will use this priority argument and showcase how it works. So priority argument, you can pass the integer values, and this, like let's say in this case I have just declared this enum high and low, and I am passing this high value which is higher than this low value. That's all I'm really doing, and I am launching in these two sequences parallelly within the fork, right, to launch them in parallel. Now, and additionally what I have to do is I have to set the arbitration policy of the sequencer to this arb sequence, UVM sequence arb strict FIFO. So I need to set this, and this one I can set it either by calling, like let's say whatever env.agent.sequencer dot set arbitration. I can do it this way also, or if I want to set it within these particular sequence, then I can use a handle called m sequencer. So whenever a sequence starts running on a sequencer, within the sequence it has a handle called m sequencer, which is assigned to the sequencer handle on which it is running. So this all happens automatically within the UVM. So you can use that m sequencer dot set arbitration and pass this particular thing. This must be passed for this particular example to work. Why I am emphasizing on that is, since I am setting the init sequence priority to be high, as long as the init sequence has a sequence item to send, it will be selected over the traffic sequence. So that's how the initialization will take place first, and then the traffic sequence will start, and that we accomplished using this priority field. And also we showcased how you can start multiple sequences in parallel, and we also discussed about this m underscore sequencer handle, which will be present within each of the sequence that's initialized with the handle of the sequencer on which that particular sequence is running. So in this case, inside the init sequence, let's say if I call this, the m sequencer handle will be initialized with the env.agent.sequencer handle, right? So that's why I said that I can either call env.agent.sequencer.set arbitration to this UVM sequence arb strict FIFO over here on the line 781, or I can do it within the init sequence using the m sequencer handle. Okay, so these are the few concepts I know you might be wondering, okay, how many concepts like this are there in UVM, right? So that is a valid thing if that question is coming in your mind. Uh, so yeah, so there are going to be multiple features, right? So there are going to be multiple flavors, and what will happen is that we are showing you few of the core things. So you start off with these, and then rest of them as and when the need arises, or when you get a periodically chance, you look up more documentation and look at more advanced UVM topics to learn more about them and use them as and when the need arises. That's the only way you keep picking up. You don't pick up everything and then start using. You pick up the core, and then rest of them you pick it up on the need basis or through the periodic upskilling. Let's look at a little bit more details of this set arbitration that we looked at. Whenever we are running parallel sequence on a sequencer, the arbitration among them can be set using this set arbitration, the function call, and this takes the this enum value, set type value, and those can be selected from one of these options. UVM sequence R54 is your default option, wherein requests are granted in the FIFO order, one after another. Sequence is selected. You can do arb weighted. We can specify the weight, and depending on the weight, they can be granted randomly. And then you have arb random, where requests are granted randomly. So this you can use it for mixing traffic from different parallel sequences randomly. You can use this. So either you can generate randomly within a sequence, or you can have set of sequences that generate random transactions of certain flavor and start them parallelly, and set the arbitration policy to arb random to get a good mix of them. And we also looked at arb strict FIFO in the previous example. So you have arb strict random, where whatever, like if you have multiple sequences with different priority, and then if you have multiple like in each of the priority band, let's say we have high priority, medium priority, low priority, in each of them we have multiple sequences with the same higher priority, same medium priority, same lower priority. Among them again you can do the random selection using the arb strict random. There's one more interesting option called arb UVM sequence arb user. So arbitration is delegated to the user defined functions. So user function, which is called as user priority arbitration, and that function will specify which is the next sequence to be granted. And the way it's done is, so you say anyway, so this we have already looked at. You can either use the sequencer handle and call set arbitration, or within the sequence you can use M sequencer and set the arbitration. And then for this one, so you set it to user arb, and then once you do this, the next step is that within your sequencer declaration, you have this virtual function availability, which is a part of your UVM sequencer base class. So a virtual function user priority arbitration, and it returns an integer. Integer is an index into a queue, and that queue is what happens is whenever the arbitration needs to be conducted, the sequencer will give a call to this particular function, and as an input argument it will pass the available sequences. So we had said that you have started multiple sequences, right? So each of those sequences, it will give it as a queue, and then you can select one of them and pass the index back to the sequencer, and then the sequencer will select that particular sequence and send it. And then the algorithm that you need to follow, you can specify your own algorithm within this function. So this way you can set and utilize the different arbitration types within the sequencer for managing parallel sequences, multiple parallel sequences running on the same sequencer. Okay, so we'll take a look at the nested sequence. So we have a class USB sequence extending a UVM sequence, and then we have a bunch of sequences within this. So we have a connect sequence wherein you connect a USB sequence, USB drive or something, like let's say we are testing a USB host controller, then you can connect a flash drive. So for that we have a connect sequence, and then we have enumeration sequence where the drive gets enumerated, it is read and get detected as a flash drive. And then you have a traffic sequence. So depending on there are a couple of endpoint type of a concept that comes into picture. So those endpoints get detected, configured in the traffic sequence. You either do a file read from that flash drive, or you do a file write, right? So those are the parts of these particular sequences. And then through factory we create the sequences and then run them in sequence, right? So we say C sequence.start, and note that we are passing the M sequencer over here. M sequencer is the handle that's present within the UVM sequence base class that gets set to the sequencer on which it has been started. So whenever I say USB sequence.start, then let's say I am saying env.usb agent.sequencer, then the env dot USB underscore agent dot sequencer, that will be set in the M sequencer. So I am passing that to my nested sequences. So I am saying connect sequence dot start, and I'm passing M sequencer handle over here. And then after that I'm running the enumeration sequence dot start, and then I'm doing the traffic sequence dot start. These I'm running sequentially, but these sequences are nested as a part of the USB sequence. So from the top level, if we view it, it will be a USB sequence start, and within that we are running these sequentially. So it looks so it's a sort of how the use case for the nested sequence and how they are accomplished. Okay, let's look at a few more flavors of the sequences. So there's this concept of reactive sequences. Can be done in a couple of ways. We'll look at one of the ways. So reactive stimulus technique allows the sequences to receive feedback from DUT and then determine if the stimulus should be sent next, like, or what stimulus should be sent next. Idea is to use the response to bias the stimulus generated, and this can be actually taken to extreme as well. That is like in the interaction that we had seen in the sequence, wherein we had done the request phase followed by response phase, right? We can totally reverse it as well. That is, we start off from the response and then we execute the request, right? For example, let's say we could build agent wherein the DUT sends something first, and then based on that we need to, let's say, respond back to it, right? And then we always have to wait for DUT to send something if we have that type of an requirement. Even for those we can build reactive type of a sequence wherein we can receive something from the monitor, and then then based on that we can be sending the stimulus, right? So those are also called as reactive sequences. We are not going to look at that type of a flavor. So here we are going to look at something wherein based on the DUTs like the response, we will bias the stimulus. So this is the like a FIFO full sequence extending the UVM sequence. So what we want to do is we want to write a sequence that writes to a FIFO till it becomes full, right? That is the type of reactive sequence that we want to do. And what is it reacting to? It's reacting to the full information that is coming in from the DUT. How we are doing it? So we are saying while not response dot full, response is the transaction that is coming in from the FIFO driver. So it is saying FIFO write FIFO transaction, and in this task write FIFO, what we are doing regular the sequence. So we are saying start item transaction, which is our request. We are randomizing and saying it should be write, and the read should be set to 0. The data would get automatically randomized, and we will send that to the FIFO driver, and that wait for the transaction to be pushed in, and then we say get response, and then in the response we check if it is not full, and then we continue to write it, right? So this way what we are doing is we are biasing the stimulus that is generated based on what is provided by the DUT. So this is the like the basic idea behind the reactive sequences. So finally, I think the last type of sequence that we are going to look at is the layered sequence. It's a very advanced concept. So we are just going to briefly introduce you to it. We will not do a deep dive into this particular area. But the idea over here is like this. So like let's say we take a protocol that contains 3 layers, right? Then what happens is the physical layer, which actually leaves the the design and comes out to the IO pin, is there's only the one layer, right? So the physical layer leaves out of the chip, but the rest of the layer, like for example data link layer, feeds to the physical layer, then the transaction layer feeds to the data link layer. So if you have that type of a protocol type of a structure and you want to model each of the layer as agents, right? So you are not only like creating a layered sequence, but in a way you are also creating a layered agents, right? So that is the much higher level concept at play. So how do you do it is, like, you will have the physical layer will be your regular agent. What do I mean by that is, it will have the monitor, it will have the driver, which will finally be looking at the actual interface signals, and then it will have the sequencer, which would be like take a high level transaction and then convert it to series of, like, let's say symbols, and those symbols are getting serialized and sent out to the DUT, right? So that is what is the lower level layer is doing. But the higher level layers, other than the physical layer, they are not directly interacting with the DUT signal interfaces. So they will not have a driver type of a concept. Okay, so they will have only the sequencer and monitor. So let's say this is the second layer and this is the third layer. So you see that they only have the monitor. They don't have the driver associated with them. So this is first concept of layering the agents. Now the idea is that the way this works is that this sequencer ultimately pulls, so the physical layer sequencer will pull the sequence item from the link layer sequence, and the link layer sequencer will pull the items from the transaction layer sequence, right? So and then each one of them do the translation to the lower layer and send it out. Like for example, I could be running let's say a high level packet, or like a high level traffic generation. Let's say I can generate up to 4 kb worth of traffic at the overall, right? So I'm saying 4 kb worth of data needs to be transferred, but let's say the transaction layer is capable of sending it at 1 kb, then it breaks those 4 kb, converts it into 1 kb, right? And then each of those 1 kb gets transmitted to the link layer, and link layer, let's say it breaks it up into 256 byte type of link layer packets and sends it up. So it takes each one of those 1 kb sequence item coming in, translates it into 4 256 byte link layer packets and sends it out to this physical layer sequencer. So physical layer sequencer takes each of those 256 byte sequence item, and let's say it takes each one of the byte out of it, sends it to the driver, which serializes it and sends it out. So each of these middle level layer sequencers, what they do is they implement some sort of a translator type of a functionality, right? So the translator sequence will be running, which takes in a higher level sequence item, converts it into a sequence item that is compatible with the lower layer, and sends it out. So this is the way the communication is established in the layered agents, and then the layered sequences are written, and all the higher level sequencers will run a translator sequences, converting from a higher level sequence item to lower layer sequence item, and the reverse happens for the monitor. So for the monitor, what happens, like the individual bytes get received, and those bytes are converted into, like, let's say a DL level packet, and the DL level packet is combined over here in the monitor that is present at the layer 2. It will combine 4 of those DL level packets and create one like a transaction level packet for the 4 kb that we had sent, and this one, the transaction level, will combine 4 of those transaction level packets and ultimately convert to 4 kb data access that has come in and send it out to the application level. So this is the way the layered agent concept is implemented, and the layered sequences on the higher layer are the only one that are different than what we have already seen, and they instead of like driving it to the physical layer, they do the translation from the lower layer the higher layer to the lower layer type of a functionality. And yes, I think for the monitor you do the connection through the analysis ports, and then implement the conversion in the upper layer monitor. So all the upper layers, they are mainly the translators. They are not doing the real the traditional agent, the way we have seen it, wherein we are directly dealing with the signal level information and converting signal level information to the transactions in the lower layer agents. But in the upper layer agents, we are converting the lower layer transactions into higher level transactions instead of converting the wire level activities to the transactions. So that is the difference that we see in the layered agents, and the same thing applies to the layered sequences as well. So we are not going to go deep into it and look at an example, but just wanted to give you guys a sense of what is really done in this type of scenarios. Okay, so now that we have covered various individual sequence patterns, let's look at the virtual sequencer and then follow it up with the virtual sequence, which is the last type of pattern that we want to explore. So first, let's understand what's a virtual sequencer. So virtual sequencer is the one that allows you the centralized control over the activity of multiple verification components which are connected to different interfaces of DUT. We have seen bunch of virtual sequences when we have looked at the bootstrapping of the UR Testbench. So by creating a virtual sequence, what happens is the existing sequence libraries of underlying interface components and block level environments can be used, and we can coordinate the system level scenarios, right? So that's the benefit. And then once you create that particular virtual sequence, you can continue to reuse and build on the top of it. So actually you can create a virtual sequence of sequences. A virtual sequence can contain further virtual sequences, so that way you can hierarchically keep building it up. So virtual sequence, what the virtual sequencer does is it has actually contains the references to its subsequencers, right? And then that is the driver sequencers or other virtual sequencers in which it will invoke the sequences, right? So a virtual sequencer can contain sequencers handles of the direct interface based sequencers as well as the other virtual sequencers. So both it can contain, and it can start the corresponding sequence or the virtual sequences that it has handles to. And then virtual sequences can invoke, as we talked about, other virtual sequences because anyway the virtual sequencer is expected to contain the handle for those hierarchically built virtual sequencers. And so and in each of the, so as well as each of the subsequences, so you can have other subsequences which you can start as a part of your virtual sequence. And virtual sequencers actually do not have their own data item, and therefore they do not execute any data items on themselves. Virtual sequence can execute items on other sequencers that can execute further the actual items, right? So it's all mainly meant for coordinating. So here we are just showing a diagram. So you can have an Ethernet agent, and you have a CPU agent. You can have a virtual sequencer which is feeding in the configuration and as well as the sequences. So once it has the handle to each of the sequencers that are present in these agents, then it can start the sequences on both of those sequencers and can coordinate them in the way the ordering that is required. So I think once we have looked at the examples, but in this context of this discussion, when we look at the further examples, it will become more clear. So let's jump into an example of virtual sequence and the sequencer. So you construct first the virtual sequencer. So you say class simple virtual sequencer. It extends from the UVM sequencer. Note that it's not parameterized by any sequence item, because by itself it's not really going to generate any actual sequence items. and inside that, whatever the sub the sequences that we want to run, the corresponding sequencer handles must be present within the corresponding virtual sequencer. So we have the Ethernet sequencer, CPU sequencer handles present. Then as this belong to component hierarchy, we have standard name and the parent inputs that are being passed, and then the super.new, all the boilerplate code. Then we are registering it to the factory. So this is the basic virtual sequencer definition. So one of the things that can be done is within the virtual sequencer, or in general in any sequencer, you can provide additional tasks and functions, because those tasks and functions can be accessed through the sequence on need basis. Okay, so that can be done. And how to do that, there is one small detail involved in it that we will talk about it when we look at the sequence. So then we are having a simple TB, and then here in this way we have the environment. Let's say we are utilizing the unit level environments to build a higher system level environment. So we are taking in a CPU environment, Ethernet environment, and then we are instancing our simple virtual sequencer as M sequencer, and then in the build phase we are constructing all of them through the standard factory calls. Nothing extraordinary, business as usual. And then in the connect phase, what we are doing is to this virtual sequencer, whatever we have constructed, the individual sequencer handles we are assigning. Let's say the virtual sequencer or CPU sequencer, we can assign it this way from the CPU environment that we have. Some specific sequencer, we are assigning it to the CPU sequencer, and then the same we can do like the way we have done it in this particular line at the 564. We can do the same one on this line number 565 using the config db as well. So we can say config db and then parameterize it with the UVM sequencer, set this dot v sequencer is the name. And it's present in this environment, high level environment hierarchy. And then we can say Ethernet sequencer is the name of the handle that's present within the virtual sequencer, and then we are assigning it with, let's say, this particular sequencer that's present in the Ethernet environment, right? So this way we can the config db will take care of updating this particular variable with a value that we have set based on this hierarchy that we have specified. So this way what we did is we did two steps so far. First step, we created the virtual sequencer within which we have declared the individual sequencer handles, and then in the connect phase we have connected those individual handles to the corresponding sequencer from the low level environments, which actually do the execution of the corresponding sequence items. Now let's write a simple virtual sequence. So we have a simple virtual sequence which extends from the UVM sequence. Again, note that it's not parameterized from any of the request or the response sequence items, because it's not going to lead to creation of any of its own sequence items. So we have the CPU config sequence, we have a Ethernet large payload sequence, and some random traffic virtual sequence, right? So we have bunch of other sequence. Then what we can do is we can use this macros. So as we have been seeing, right, wherever we have a multi-step process, like for example, with respect to a sequence, what do we have to do? Like we have to construct that particular sequence using the factory, then randomize that particular sequence, and then call the start, right? That's what we need to do with the sequence. So instead of having to do those 2 to 3 lines of code, you can, even when you randomize, again you have to check. So all that code is a very repeatable code. So those you can do it with the help of these macros. So here we are using this tick UVM do on. We are passing this conf sequence, and then we are saying run it on a p sequencer dot CPU sequencer. So p sequencer is like we have seen M sequencer sequencer, for example, right? So M sequencer is a handle that contains the pointer to the UVM sequencer on which that particular sequencer is running. So there's another concept called P sequencer. So P sequencer and M sequencer, the difference being the M sequencer handle type is a standard, just like a base class handle type, like a UVM sequencer, but the P sequencer will be of the type on which the actual sequence is running. For example, we would be running this simple virtual sequence. It will be running on this simple virtual sequencer, right? So it will be running on this particular sequencer. So the P sequencer will be actually pointing to the data type of a simple virtual sequencer and not just a UVM sequencer, right? So that would be the difference. So what happens is the reason why we want to do that is sometime if we declare some methods over here inside this simple virtual sequencer, those become accessible with the P sequencer, because P sequencer is a handle of the type simple virtual sequencer and not of like a regular base class handle. It's not just a UVM sequencer handle, it's a handle of the type simple virtual sequencer. So because of that, it is more useful, so you can use that. Here in this example we are not using it, but you can use this handle to access the any methods that are present within this particular virtual sequencer via the sequence, right? So you can then access any of the Testbench related features. The methods could embody them, and through them you can access more features within the sequence. So then you do just say tick UVM do, and you start your virtual sequence. So now a virtual sequence is starting these couple of the regular sequences which will run on a actual sequencer and generate the transactions, and it can also start a virtual sequence as well. So this way it can be composed, and you can coordinate the traffic on a different interface by reusing the low-level environments. We had used these shortcut macros like a to tick UVM do on or tick UVM do, and all these are present within this sequence defines.svh that's present in the UVM source code. Just wanted to show you that this is the documentation reference. You can refer to these in the UVM the standard base class library documentation to understand, and there are even more such shortcut macros that are available that saves you writing some repeated code. These are the ones that are used for creating, randomizing, and sending sequence item or a subsequence. So these are the macros that you can utilize. There are many more, right? So I'm just showing you a few of them to give you a flavor, and I just wanted to show you a little bit of the code. This is the source code snippet that I have captured from this UVM sequence defines.svh. What I wanted to point you out is that ultimately, I mean, don't think that, don't feel that, okay, you don't know what's happening inside, right? So I just wanted to show you. So it's checking, like, for example, it's randomizing the sequence, right? So there are a bunch of conditions, don't worry about it. If you look deeply, you'll understand. But what it is doing is it is randomizing that particular sequence and then starting the sequence, right? So that's what you would do, right? So that is the you will create the sequence using the factory, you'll randomize it, and then you will start it, right? So that's what is really happening in these macros, and all these macros eventually use this internal macro, and I'm showing you the code of that to give you a sense that you could have done it this way, but just saves you these like a 4-5 lines of code by using these macros. This type of macros are available even for the implementation within the sequence, like whatever we did, the start item and then the finish item, even like the start item, randomize, finish item, even for that particular sequence. The macros are available. Yeah, I mean, it's a personal preference whether you like to use the macros and save some coding, or you really like to code it out. Sometimes if it's a very regular pattern, you don't intend to control much, then the macros are much better. But if you think that it's going to be tricky and you might have to debug something in the middle, then when you use it as a macro, like sometimes the debugging can become tricky. So that is something that those are the trade-offs that you need to keep it in mind to decide whether to use the macro or to use the the regular the n number of lines of code. But you need to be aware at least that there exist these shortcut macros or the sequence macros. For every function there are a bunch of macros that can be used which save you some level of the coding effort. So keep that thought in your mind, and as and when you need it you can refer and use it if you happen to do it very frequently. If you are frequently writing the same code again and again, then you can probably use these macros.